So now we have see those numbers. Of course, for the users, we can never access all the items in the system. So if you look at the table, it's like a lot of like empty entries, right? So it's kind of very sparse. So the goal is that we try to learn the latent representations for the users and the items such that those latent representations can recover this matrix as accurate as possible. Okay? So that's why we can further decompose that matrix into two smaller matrices. One is called U, so it's like number of users times number of dimension, right? And a matrix V, which is number of items times number of dimension. So each column here actually is a representation, low dimensional feature representation for users and items. So once we have this low dimensional matrix to represent U and V, then we can just do kind of dot product for each user and item pair. Then we can fill in all the entries in the left matrix, right? So we can estimate, okay, for unseen pair, user item pair, what will be the score, rating score. So that's actually is kind of the starting point of collaborative filtering method. So it is just based on matrix factorization. Okay, so that's the starting point. So now, when we look at the real world, what would be the challenges? Okay, why we cannot just use the simple matrix factorization to do the recommendation? Okay, so there are a bunch of challenges. The first challenge is that if you look at the real world, right? So we know that in many cases, for the users, especially for the users who just join the system, okay, or for the items like movies, new released movies, actually you cannot really collect a lot of interaction information for them. So this is called like cold start problem, okay? And also if you look at the matrix I have shown in the previous slides, you will see that it actually is very sparse. So now how we can overcome the sparsity issue and the cold start problem, okay? So essentially we really need to utilize additional information to make sure that those long tail users and items can be covered. So that's the first challenge and the possible solution to it. And the second challenge is that for the users' items, okay, in addition to the interaction between them, actually you also have a lot of content information, like text, right? So like in LinkedIn data, actually you do have the text description for user profile and for the job profile. So how can we leverage that kind of text information to do the recommendation, which is also very important. And lastly, okay, in most of the cases, we just assume we do recommendation, recommend those items, right, without like location, spatials. That's just like in the online world, we want to do recommendation. But in practice, the recommendation can really depend on where you are at which time. Okay, so the spatial-temporal, those features becomes very important. And how we can utilize those kind of information and help us to do the right recommendation, that's the third challenge. Okay, so those three challenges will be covered by the three parts in this tutorial. So, but general, if we look the solution in a unified framework, we still think that probably we should look at the recommendation task or the data that we can collect for recommendation task as this heterogeneous information network. So in addition to the users and items and the interactions between them, we actually do observe other types of data, right? So for example, for the movies, they are also linked to like directors, actors, actresses, right? And the movie itself also contains a lot of text information. For example, the description of the plot, right? And you also can see that between those additional entities, actually there are also different types of relationships. For example, for the user and user, suppose you have the friendship relation between them. Definitely you can leverage that information and help you to do further recommendation, right? So now I have talked about information network. So here another 101 introduction to what are information networks. So essentially, when we say information networks, then we have the nodes and we also have the links. So what are nodes? So actually nodes represent the real world entities. Okay, and what are links? The links actually represent in a relationship or interaction between them, right? Like the user friendship link and user has watched some movie, this kind of interaction link, and all kinds of those links, right? And also we try to emphasize that in most of the real world cases, the information networks are heterogeneous. So in other words, we have not just one type of nodes. So like in the traditional social network setting, probably you see that, okay, we have people and we have the friendship between them. But in the real world, especially in the setting of recommendation, you have like different types of nodes and different types of links as shown in the previous slides and also in this slide. Okay, so for example, we have people and they kind of watch TV, watch a movie and read books and purchase some products. Okay, they're doing all kinds of things. Actually, in practice, all these behaviors can be modeled as different types of relationships. And these different types of relationships will help you determine which movie you will like. So which book you read and which TV you watch is helpful to determine which movie you will like. Right? So, but of course, in real life, it's very difficult for us to get all this information. But as long as you get some additional information, try to integrate it into your recommendation system. So this is not just for the commercial system that you can do the recommendation. Like in the biomedical domain, okay, for example, in this one, so essentially you can also extract entities related to medical concepts like patients, disease, drugs, right? And also between those concepts, you can have these different interactions, like a patient has some disease and carries some gene, something like that. So you can do drug recommendation. Okay, recommendation is not just designed for commercial system. It can be used for many other very interesting tasks. So this is just a introduction, a preliminary of what are the information network and why we think that the information network carries a lot of additional information and we really need to leverage them to do the better recommendation. So now let's come to our major part. So given that we know, okay, it's a heterogeneous network and how we can do recommendation. So essentially for the first real part, it contains 4 different directions. The first direction is that how we can do hybrid collaborative filtering with this additional side information network information. Okay, so we have seen this picture before. So essentially, we have discussed that for the existing recommendation algorithms, we can categorize them into different groups. The first, if we just use user item interaction data, then it is called a collaborative filtering, right? If you are just using the content information, then it's content-based recommendation. And if you combine all those information in addition to some external knowledge, which can be modeled as heterogeneous information network, then you can propose this hybrid recommendation algorithm. So in our case, okay, so for part 2, so we essentially try to integrate 2 types of information. One is the user item interaction. So that's why we still call it collaborative filtering, right? The second type of information is this additional external knowledge. And this external knowledge is represented by this heterogeneous information network. Let's see that how we can combine the 2 to do a better recommendation. So now essentially, if you look at the problem, you will think that we have user item, this kind of network, and the users and items, they are kind of embedded in some other bigger network. So they connect to other entities with other different relationships. So how we can leverage those information? So before us, actually there are some interesting study try to utilize some network relationship to further enhance recommendation, but they didn't really consider the heterogeneous setting. But now let's check this picture. Okay, so this is like a very nice example. Try to look at this recommendation task in a heterogeneous network view. Okay, so we have users and items, their interaction, and items are linked to many other different entities, and they are linked with them with different types of relationships. And between users, you can also have all kinds of relationships. So let's see why those additional information can help, right? So traditionally, we do not have additional information, just a user-item interaction. So why the additional information can help? Because if we just look at the user-item interaction, you will see that most of the users and most of the items, they actually in the long tail part. So they do not have too many connections to other things, like users, right? Most of the users probably just watch 1 or 2 movies. And for most of the movies, they just watched by a very small number of users. Okay, so we have faced this very severe data sparsity issue. And why we think the additional information can help? Because if we embed this user item interaction in a much bigger heterogeneous information network, then we can connect the users to the items through different types of relationships. Okay? So it's kind of different types of relationship can complementary each other, provide different aspects of information for the user and for the item. Okay, so that's one thing. And the second thing is that because the user and items can connect through different connections, so somehow we can propose personalized models to do the recommendation. Okay, so far you just accept, okay, there are 2 advantages, but how we can do that, let's move on. So this is an example, like for all the 3 users here, 3 groups of users here, all of them love the movie Aliens. Okay, so at this moment, probably you think, oh, we just do the same recommendation for them. But if we go deeper and try to understand the reason why the 3 groups of users love the same movie, the reason would be rather different. Okay, for example, for the blue group, probably they are just the fans of the director of the movie. They just watch all the movies directed by James Cameron. Okay, and for the second group of users, red group, probably they just like the science fiction movie in the 80s. Okay, and for the third group, probably they just love the actress played in this movie. So they really have different reasons, right? So for the traditional collaborative filtering, essentially cannot really capture those different reasons, okay? And so that's why we think that by using our methodology, we can do personalization. Probably you will argue that, saying that in the traditional recommendation algorithm, the traditional collaborative filtering, we already do personalized recommendation, because for different people, we're going to recommend different things in general, right? But for that one, it's very different from our personalization, because for that one, it's just that we have observed different interactions for different users. Okay, so it's like at the data level, we have observed different things. So that's why we can have different representation for you, and then we have different recommendation to you. But at the model level, for the traditional collaborative filtering, this is just a one model. Okay, if it's just a one model, there's no way for them to really distinguish the different reasons. And for us, we're going to provide different models for different groups of people. So it's truly at the model level, we're doing this personalized recommendation. How we can do that? So let's move on, okay? So the main idea is that the preference of a user to an item can be propagated in this heterogeneous network. Okay, so in the traditional setting, we just observe the user and the items, right? So, okay, so if a user likes a movie, then that's it. But now in the heterogeneous network setting, we can expand this, okay? So, for example, here, so this is something we have observed. Alice loves the movie Titanic. But if we know that the Titanic has been watched by some other users, and this user like loved this actor or actress, and this actor or actress played in another movie. So actually we can have a path become kind of manifest from this user to King Kong, this new movie. And this kind of connectivity, okay, is propagated in this heterogeneous network. And this interaction is kind of extended interaction. It's not observed in our original data, right? And similarly, we can do another kind of propagation. Suppose Charlie and Alice, they're friends. So very likely you will love the same movie loved by your friends. So then we can do the extension here. So we can also record a kind of pseudo interaction between Charlie and Titanic. Okay, so initially this user item interaction is very, very sparse. But after this kind of propagation, right, you have collected so many interactions between user and item. They are unseen before. Okay, and also because the propagation are very different from each other, right? So here, user to movie is one type of propagation, and user movie, user actor actress to movie is another type of propagation. Of course, like you can do another way. For example, user movie, actor actress to movie, right? So you have different types of propagation. And this different types of propagation actually captures the different reason that we think you are likely to love a new movie that you have never seen, right? So for this one's like I have explained, because you're friends, so we think since you're friends, you may share some similar interests. So that's why you're going to love the same movie. And for this kind of path, you will say that, oh, because these two movies are started by the same actor or actress. So that's why I think you may also consider to watch this movie. So different types of propagation actually represent different types of semantics. And that captures the reason that why I want to do the recommendation. Okay, so our algorithm is just based on this propagation. So now we can really enumerate different types of propagation paths. Okay, for each different propagation path, we actually can prepare a new user item interaction matrix. Right? So because it's just if we do propagation in the network, it's just a kind of matrix multiplication. So we can, starting from this original user item interaction matrix, for example, we times the item interaction matrix, that's going to be a new user item interaction matrix. So we're going to have new user item interaction matrix. And after we have this new user item interaction matrix, we can again do this matrix factorization. But this matrix factorization is no longer based on the original user item interaction matrix. Now it is based on this propagation-based interaction matrix, right? So for each type of interaction matrix, actually, you can do a matrix factorization, and then those ones, it could be considered as the latent representation that implied by that type of propagation. Okay, yes?
But wouldn't you end up with a huge number of matrices?
Yeah, that's a very good question. So usually we want to specify the length of the path we want to go. We don't want to let the propagation go to very far away places. Okay, so we just specify a length, then we can enumerate, okay, how many possible user item paths we can have.
And do you specify the actual path, or as long as it's, or the only constraint is the length?
Length. Yeah, so a very simple way that we just specify the put some constraint on the length. But you can do some other like feature selection to see.
Because it's just the length and the semantics are different.
Right. So
So the matrix would not only
Exactly. So actually, even the length is the same. If you propagate it differently, the semantic is also different. So that's why we really need to differentiate those different new user item interaction matrices.
Yeah, this is why after you separated them.
Separate them, yes.
Because they carry different semantic meaning.
Exactly.
But then you said the only constraint is the length.
Yeah. So for example, if we constrain the length as 4, then probably there are 10 such different, we call it metapaths, 10 different metapaths. Yeah. So we need to separate those 10 different metapaths. So for each metapath-based user item interaction, we're going to do matrix factorization. They will be considered as the latent features that can be extracted from this particular metapath. So now, once we have this feature representation for the users and items on the different metapaths, then the question that how we can combine them. Okay, so here we do a very simple combination. We just do linear combination, weighted linear combination. So essentially, how we can do recommendation, right? So essentially, we wanted to know that what's the similarity score between a user and an item, right? So if there is just one user item interaction matrix, we just do like U times V, that's it, right? But now we have like different metapath. We have different such kind of multiplications. So that's why we need to put a weight here. And this weight should be learned because we want to know which metapath is most important for this recommendation task. Okay, and that weight is going to be learned through the data. Okay, so this is a score function. Okay, and later we're going to discuss how we can learn it. But now, let's say, if we just wanted to do this global recommendation, so it's like propose one global model to do the recommendation, then that's it. Okay, just a one model. But we say that in our model, under our framework, actually we can really leverage the reasons to do recommendation, and we can learn a different weight for different group of people. So in other words, different group of people will love the same movie for different reasons. Okay, so that's why in addition, instead of just propose this like global recommendation model, we kind of first try to do some clustering for the users. Okay, and then for each user group, we wanted to learn a separate weighting, importance weighting. Okay, so that's the general idea. Now let's first say that if there is just a one model, okay, what will be the upper function? So in this case, we consider it's an implicit feedback. So in other words, we only know that whether this user watched the movie or not. Okay, we do not observe the exact rating score. So we're considering this case. So essentially, once we know the score function between a user and item, which is defined in the previous slide, then the task is easy, right? So we just prepare those triplets. For a user, we prepare two movies, okay, A and B. So A is some movie that I have watched, and B is some movie I haven't watched. So of course, I hope to rank the movies I have watched higher than the movie I haven't watched, right? So essentially, we hope that the score function between user I and item A is higher than user I and item B. Yes?
There are much more unbuilt movies than built movies. So you sample the negative samples.
Yes, very nice question. Yeah, we have to do negative sampling somehow. So essentially, you can prepare so many negative pairs. But here it's more like we prepare triplets. It's like for one positive pair, we prepare just another negative pair.
So it's just a randomly sample?
Right now, we just do random sample. So yeah, for sampling, well, yeah, actually we will discuss something related to sampling later. But here, it's just a uniform random sampling. Okay, so based on this idea, we can form this upper function, and then we'll put some regularization on the theta part, because theta is something we're going to learn. Okay, so essentially for the home framework, it's like we first clustering the users based on any very naive clustering algorithm, and then for each group of user, we try to write down the upper function, right? So then we can learn separate the theta. And then once we learn the theta for each group of user, then we plug in back here for the personalized model, because here we need to know that for this particular user, it is like with some percentage belong to some group, and for that group, you're going to use the weight learned from that group. Okay. So then we can do the recommendation. So far, any questions? Okay, so then we compared our proposed methods with some others, like do not, first of all, compare with method, do not leverage those additional information. We also compare our method by doing this flat concatenation of the existing information. So like hybrid SVM, just to put those sparse link information as flat vector. It turns out that our methods are much better, okay, and also personalized recommendation is much better than the global model for recommendation. So in other words, you really needed to kind of provide final level recommendation model for the smaller group of users. Okay, so that's a very important lesson. And also we check some other details, like when our model can do a better job, right? So it turns out that we still expect that the user have a relative higher number of interactions with those items. Okay, although the performance can be enhanced a lot, but if the user just interact with one item, even you do some propagation, still not that good. Okay, but compared to other algorithms, we do not need to have that many items, but still not too tiny. Okay, and also when personalized model work better, it's like for the user, you have to have some personality. Okay, you cannot just watch a movie that are popular. Then in this case, it's very difficult for our personalized model to do a better recommendation for you. Okay, so that's some interesting conclusion. So any questions so far? So in the previous work, so we have introduced one way to utilize the additional information, right? We just propagate the user item preference over different paths, over different meta paths. And I wanted to learn which meta path is most important or not. So actually there are other ways to try to utilize this link information, that is from a graph regularization point of view. Okay, so what is graph regularization? So the essential idea is that why there are links between people, for example, okay, why you make friends with other people, most likely is caused by homophily. So essentially, the two entities share some similarity, right? So we wanted to utilize this heuristic. And how to utilize it? It can be captured by the so-called graph regularization. So essentially the idea is that suppose two nodes have some like latent representation, which is indicated by Fi and Fj, okay? Then if there's a very strong tie between those nodes, which is denoted by Wij, okay, then we hope that the difference between Fi and Fj is as small as possible, right? So it's graph regularization. Or in other words, it's another way to interpret homophily. We really hope that the connected nodes, especially those strongly connected nodes, they are similar to each other. And this can be captured by this formula. Okay, and this formula can be further, you do a little bit derivation, and it can be written in this form, like graph Laplacian form. Okay, so probably I want to skip the detail because here I just want to convey the main idea. Okay, so essentially I want to force the entities that are connected are similar to each other. Okay, so now let's let's start with a very simple example. So here we do not consider heterogeneous links. Let's just say we have this user item matrix here, and we only observe one type of link, which is the friendship link between the users. Okay, so now this is a traditional collaborative filtering for recommendation, right? So it's just a user item rating matrix. But now we also have this social network information between users. Okay, so how we can combine these two together to do a better recommendation. So why we think that is helpful. So in the previous work, I have already said some things like because we think you and your friends share some similarity. So we think that more likely the movie liked by your friend is also going to be liked by you. Okay, so that's the intuition. So now let's see how we can apply graph regularization to enhance our recommendation task. So essentially, we're going to combine two objective functions. The first is still the matrix factorization. So essentially, we hope to decompose the rating matrix into two smaller matrices, right? So that's the first objective function, and we hope that the error is minimal. And also, we hope that the two connected friends, their latent representation is as close as possible to each other. Okay, so there are two forms of how can we utilize the link information. So here, I will focus on the second part. So the second part is essentially the more standard graph regularization. So essentially for each link we have observed between two people, then we hope that the latent representation is as close as possible to each other. And then we'll put some other regularization here. So essentially we have proposed a new upper function, which just the integration or combination of two smaller goals, right? So the first goal is the standard collaborative filtering goal, and the second is the graph regularization goal, okay? And then since this latent representation for users is appear in both of the two parts, so it will be learned jointly, okay? And for this, how to define similarity part, I will skip it. So now let's just look at the result, okay? So it turns out that if we add those social relations, and the recommendation performance can be much enhanced, okay? And there are two types of ways to do the social regularization, and I said that I just focus on the second part, the standard graph regularization part, because that one, if you look at this last two columns, actually they are much better. And how to determine the strength of the ties between people in the social network, it turns out Pearson correlation is better than the cosine similarity, but that is just the details, like how to determine the strength of a tie. Okay, so it's just a WIG. Okay, so that's something that the people already do for this combining one single relationship to this user item interaction. But in real world, okay, still think about that heterogeneous movie network in mind. So a movie actually is connected to many other different types of entities, like directors, actors, even text, right? So from a user side, of course, it's also connected to many other entities, but to be easier to deliver our message, let's just consider the movie side. Okay, but it's similar we can do on the user side. So for movie side, actually you can decide the similarity between movies through different meta paths. For example, movie, director, movie, okay? It represents the similarity between two movies. Why they're similar? Because they are co-directed by the same director, right? So they share the same director. And we also can use something like movie, actor, movie to say, oh, this movie, two movies are similar. Why? Because they have the same actor or actress. Okay, so you can do this a lot, right? So if we confine our length strand as 2, then we can do movie and pick any type of entity here and go back to movie. Okay, it's kind of length 2 meta path and can determine the similarity between two movies. Okay, so essentially, somehow we also want to do graph regularization based on this movie kind of similarity network, right? But we have so many. So previously we just have user social network, but now we have so many. What should we do? Okay, so that's why we really need to learn the importance weight to each possible similarity network. Okay. So essentially we have users and items, and suppose we fix some metapaths, then based on that metapath, we can determine the similarity between two movies, right? Which is called SL. And suppose we have length constraint, then we can enumerate all the length to metapaths. Suppose it's L, okay? Then we'll have L different similarity matrix between movies. So now how we can accordingly write down our object function. So for the first part, it's very similar to our to other people's work, right? So just combining the collaborative filtering part. We wanted to do a decomposition for the reading matrix. Okay, we still have just one reading matrix. Okay, and in the second part, in the previous work, people just combined with one graph regularization, right? But now we have so many different movie similarity matrix. So that's why here we needed to do we need to put this graph regularization on different matrices, and we also need to learn the importance weight to each similarity matrix because they have different semantics, right? So it's like whether the co-directing similarity is more important than the co-acting similarity, right? We do not know. We need let the data to tell, and also we need to put some regularization on that. So it turns out that this previous upper function, if we do some derivation, then it just goes to this graph Laplacian. Okay, but now we need to do a linear combination of the graph Laplacian because we have different types of similarity matrix. But the learning part, trust me, is very standard. Okay, so now let's look at the experimental results. So here we kind of consider different percentage of training data set, and I wanted to see that whether we can do a good job on the remaining test data. So what are the data here? They're links, right? They are user item links, and we're going to predict the reading score on those links. Okay, so it turns out that if we just use user item, okay, matrix, that is the performance. But if we combine the different types of meta path into the graph regularization part, our performance will be much better than those existing methods. So in other words, we indeed need to add those graph regularizations, and indeed we need to learn the important weight for those different types of similarity matrices. Okay. So this is another way to combine the heterogeneous network into the traditional collaborative filtering. So it's based on graph regularization. Okay, the first idea is based on the user preference propagation. Okay, so that's kind of different. So any questions for this one? Okay, so now I'm going to go to the third part. So more recently, so for the previous two works, actually if you look at how we utilize the network structure, we are doing either propagation or we are using metapath, so we need to like pre-compute the similarity matrix, which is very, very time consuming. Because when we try to compute those metapaths, essentially it's like matrix multiplication. Okay, so after several hops, you will see that this matrix becomes so dense, although initially it's very sparse. So computational-wise, it's very, very challenging. So more recently, there's a technique called like network embedding. So essentially, people wanted to use very efficient way to map the nodes in the network into a low-dimensional feature vector, right? So once you know the vector for each node, then you can use traditional methods to do whatever you want. Okay, so here we're going to show that actually this idea can be applied to recommendation as well. Okay, but unfortunately for most of the standard network embedding, people do not consider the task afterwards. That's like, okay, give me a network, I will give you general purpose embedding. And whether you're going to apply the embedding to do classification, clustering, recommendation, I don't care. Okay, so this work, we're going to show that you should care. Okay, you should propose this task-guided embedding. For different tasks, you really need to generate a different embedding. Okay, and that will give you best performance. Okay, so for this one, because the network, we want to play it on a much bigger network, so we no longer utilize the movie network. It's usually very tiny, right? So here we use DBLP, and we consider a very similar problem to recommendation. Essentially, it's like we want to guess who would be the true author for a paper, like in a double-blind review setting, right? So you do not know the authors of a paper, but you can observe title, abstract, and the references, and the venue, and the year, those information, right? So you want to guess who is the true author. But essentially, you can also consider like a paper is kind of item, and item linked to many different kinds of other entities, and then you wanted to see whether the item can have a link to a user. So essentially, this technique can be applied to recommendation. So now, what should we do here? Okay, so first of all, here, just to give you an idea why we think we have to do a task-guided embedding. Okay, because we know that for a network, okay, given different tasks, actually it implies different similarity that we required. Okay, a network is very complicated. For different tasks, it can give you different things. For example, for movie recommendation, probably you need to embed them in this way. Okay, but if your task is going to be like voting prediction, so essentially we're interested in your ideology, right? So probably we need to embed them in this way. So these three belong to the same group, but in the first case, those three belong to the same group. It's sort of different. How we can just provide a general purpose embedding to solve every task, right? And the second challenge is that, again, for most of the existing work, when they say, okay, we're doing network embedding, we wanted to assign some numerical feature vector to the nodes in the network that it can preserve the network structure. But they just preserve this homogeneous network structure. So they just consider setting like maybe a social network, okay, or any co-occurrence network, just one type of nodes and one type of relationship, okay. But now we have different types of nodes, different types of relationships. How we can leverage those information and try to like learn the best embedding, okay. So our solution essentially two components. Okay, the first component is that we want the task. So in our case, actually we want to do some sort of link prediction. And yes, in our mind, recommendation can be considered as a link prediction problem in information networks. Okay, so essentially the first part is like we wanted to do the link prediction. We hope that our embedding can directly make the two entities that it has this specified link as close as possible to each other, right? But remember, why we think it's task-guided, why it is task-relevant. So suppose this time we're interested to see whether the author has written a paper, right? So then we need to force these two nodes as close as possible to each other. But for different tasks, let's say, which paper I should cite for author, right? So essentially that's very different because the labels are different, the semantic of the link is different. So the things that you wanted to force them to close to each other would be rather different. So for that part, it is very depend on your task, okay? And for the second thing that you cannot just completely trust your task to force things to going around. Why? Because how many papers an author can write in real life, right? But potentially, how many papers you wanted to write, Okay, so that's a very different story. So that's why if you just directly use the observed pair, author-paper pair, it still have this sparsity issue, right? So that's why we want to utilize the remaining of the network. So for example, my student, Ting Chen, has written the paper with the keyword heterogeneous network embedding. But according to the remaining network, suppose the citation between keywords, so keyword including some paper cite another paper include another keyword. So we have the keyword citation. So we see that heterogeneous network embedding actually cite another keyword like no representation frequently. So we know that, oh, these two keywords actually are quite similar to each other. So next time if Ting Chen wrote a paper with a keyword no representation, then it's not a surprise, right? But if we just look at an existing like author paper link, you can never observe that kind of information. Okay. So that's a general idea. So that's why we wanted to combine the two things together. One is like task-guided embedding. The second is like the general purpose embedding that can utilize the remaining of the network structure. So for task-guided embedding, we don't want to make it too difficult. Okay, because indeed, people can do all kinds of feature engineering and design very fancy model, right? But then there's no purpose for us to further do the network embeddings. Why we want to do network embedding? Because we want the data to take care of everything. Okay, the model just learn important things from the data. We don't want human to do a lot of tedious work to extract those features, right? So for the task-guided embedding part, very simple. So for each paper, it's linked to some observed entities, right? So we just take a weighted average of those linked entities embedding and project its embedding as that function. And now, once we have the embedding for a paper, and we assume we have the embedding for the authors, then if there's a link between this paper and another author, we just force them to be close to each other. That's the general idea. So for the loss function, we use the Hongzhi loss function with margin. But similarly, it's like we want to sample some triplets. Okay, for each paper, we sample a positive author and a negative author. And we hope that the positive author ranks higher than the negative author in terms of the similarity calculated by the embedding. Probably we can use the dot product, right? So that's the first part. Very simple, just to force them to be close to each other, use the embedding to compute their similarity. And the second part is that we want to use the remaining of the network structure to do the general purpose embedding, okay? So how we can do that? So essentially the idea is that giving a meta path, suppose it's a keyword, cite keyword, this meta path. The idea is that given the embedding at the embedding space, okay, if we have observed some paths from keyword 1 to keyword 2, they should be close to each other in terms of the embedding, okay? So we just write down this kind of probability. So what's the probability that can, starting from a keyword 1 and reaching keyword 2 under this particular keyword citation meta path? Remember that if we switch a meta path, the observed connectivity between the keywords will be totally different. Okay, so in other words, for different meta paths, actually we can learn a completely different embedding. So now the question is that for this particular task, we're going to predict who is going to be the right author for the paper, right? So which meta path we should use? That becomes a tricky thing, okay? Let's first forget about that. Let's just say, okay, we have already know which meta path to select and to learn the general purpose embedding, and let's put them together, okay? And suppose we know that, then if we do the joint learning, we can learn a good embedding. And if we know the good embedding, we just plug in back into our task-guided embedding model, then we can know that, okay, which author is most similar to which paper, then we can do the prediction, right? So how we can select a meta path? So originally, we wanted to learn a weight like in our previous two tasks. So in the user preference propagation and the graph regularization, those two works, actually we try to learn the importance weight, right? So initially for this one, we also want to do that, but then we failed, okay? So it turns out the embedding is so sensitive to those weights, okay? So even with the grid search, it's very difficult to identify what would be the best weight. So then we say, okay, if we cannot really learn those weights, how about we do selection? Okay, we rank them. Instead of learn a weight, we just rank them. So we propose a very greedy strategy. So essentially, suppose we have a candidate metapath pool. We just every time include one of them and try to see which metapath can best enhance the link prediction performance. Okay, so we can rank them. After we rank them according to the link prediction performance, then we gradually add one by one according to their rank. So we first add the best metapath in to learn the general purpose embedding, and then we add the second best metapath in. Okay, and turns out that after some metapath, if you still want to add another one, the performance dropped. Okay, it's not like in our previous thought, like if you include more information, okay, actually your performance is going to be better. But unfortunately, if you include those unrelevant information for this link prediction task, the performance is going to be even worse. So that's a lesson. Yes.
So the link you want to add is from paper to author?
Yes. In this case, it's like paper to author, and the semantic meaning is that whether the author has written that paper.
Okay, then the question is from paper to author, I feel there will be tons of things, right? I mean, from the paper that, from all of the nodes in the paper network and also all of the nodes in the, the author network, then how do you actually rank all of those?
Okay.
You have millions of users and millions
So
of
in this case, we're not, first of all, here for the metapath does not have to go through paper to author. It could be like keyword, cite keyword, or author, co-author with author. It does not have to be starting from a paper and ending with author.
So you mean in L, for example, if there are L networks, then you mean any node more
Right.
those networks?
And yeah, so yes, any nodes. And then it's not, when we try to rank them, we're not rank like keyword 1, cite keyword 2 at this level. We're not rank at the instance level. We're rank at the metapath level. So it's like keyword, cite keyword, that will be called one type of path.
Right.
Yeah, so we just rank that. So given a length constraint, there will be not too many.
So you mean from one keyword to another keyword?
Yeah, so that's one possible. For example, it's here. Keyword, cite another keyword, right?
So you constrain your link into only the keyword network.
That's one possible candidate metapath. You also can consider like the references in your paper. So which references are you likely to use for author? That's also kind of a metapath. So also cite paper.
What do you mean by metapath? I was thinking
Metapath is a high-level connectivity to describe how the entities are linked to each other. Like author linked to paper, linked to author, it's called a metapath. It's not a concrete path. Like Jim is a co-author to Anne, it's like concrete path. Okay, this concrete path actually is co-authorship. And it can be described by author, paper, author, this metapath. Okay.
so from paper author, this will be this is not the author metapath because they have a direct link.
Paper author is also a metapath. So metapath could be direct link or like concatenated path, but it's not a concrete path.
What do you mean a concrete?
So it's like, are you familiar with database schema?
Yeah,
Yeah, so if so metapath at schema level. So if you're talking about, it's not talking about a concrete row in that table. It just tell you, okay, for this relation to describe those different columns. So it's kind of high level description. Yeah. Yes.
So when you do this additive greedy additive paths, which ones do you choose first? Do you have a particular order? Or?
Yeah. So how we can have this order? So essentially, initially we have a candidate pool for all the metapaths. So we just combine our task guided embedding with this one metapath based general purpose embedding and see which metapath performs the best, so we can rank them.
Oh yeah, so you take the first one, the best one.
Right. We just add every time initially.
Would the direct author to paper path be the strongest one?
Very nice guess. So if you look at the most important three metapaths, it's like the references typically used by author and the keywords used by author and author paper. This kind of relation. That
So
are
it's
the
like a feature selection here, so it's kind of.
yeah, it's kind of feature selection, but it's not the traditional feature selection, right? But the high level indeed is a feature selection, but it's kind of because in traditional feature selection, it's like you have like a vector data, right? All these attributes, you want to select those features. But here they are kind of connectivities in a heterogeneous network. What kind of connectivity you want to trust for this particular task? Here, the main message is that if your task changes, the selected metapath will be rather different. Okay, so that's also a reason why the general purpose embedding itself is not good enough. So if yeah,
I just want to
sure.
how many data, for example, in the data that you are measuring the performance, how many candidate links you are considering?
How many metapaths?
Yeah, how many metapaths?
So essentially, we'll consider this many metapaths.
But in the candidate pool.
Yeah, so it's all the you can use some like heuristic or length constraint to select to determine your candidate pool. So these are just the candidate pool, and we need to rank them first, and then gradually add those metapaths one by one to our joint model until the performance deteriorates. Then we stop.
So there are many.
So many, not so many. Yeah,
Fewer than I thought. For example,
yeah.
even keywords, it could be a lot.
So keyword, remember, it's just a one type of node, okay? And you also need to make sure which one is reasonable. Like keyword, site keyword probably is reasonable, right? But if you're saying keyword to venue to keyword, probably it's just too diverse. Probably it's not that reasonable. So it's like length constraint plus some heuristic. Yeah.
So you add those and then you train the model.
Yes, exactly. So that's why we see that if you compare the results with like other methods, so the first part is like feature engineering. Okay, people are still smart, so they're doing a great job. So if we just do the link prediction use a task-specific embedding, okay, because we're using very naive way to force things together, it's not good compared to the feature engineering. So essentially, if we do fancy feature engineering, it's indeed much better than using like a rough model, build a rough model. So if we just do the general purpose network embedding, interestingly, they're already comparable to the feature engineering, and sometimes are slightly better. Okay, but for our method, it's like we're using the task to guide the information selection in this heterogeneous network. The performance is enhanced significantly. It's not a marginal, okay, it's significantly. So in other words, we really need to adjust the embedding by a particular task, okay. So do you still have questions for this one, the third one? So then, if not, probably I will go to the last one, okay. The last one, slightly, okay, so the flavor is different from the previous three tasks, and it's also a paper accepted in this year's KDD. So this one is talking about how we can further enhance the speed, okay, when our club filtering involves some very complicated computation, like deep neural network kind of computation, okay. So this is a very, very unique angle, okay. So all the previous work tried to kind of enhance the performance, right? So this one's like without affect the performance, can we enhance the speed. Okay. So now let's consider setting. Suppose we're doing news recommendation. Okay, so we know that for news recommendation, if we directly want to use collaborative filtering, this kind of method, it's going to be a disaster. Why? Because news are kind of coming every hour, right? So the cold start issue is going to be very severe for news article recommendation. So what do we need to do essentially is like, instead of using the link information, we really need to take care of the content. But since this work, we really do not really talk about how to deal with the content, which will be covered in the next part. So here we just talk about the efficiency part. Okay. But the general idea is that if we can map the content into some embedding, okay, into some representation, and at the same time, we map the user into some representation into the same space, then we can just compute the similarity between the two vectors and determine which news article to recommend to this user, right? So how to map the user to some feature vector? Actually, matrix factorization is doing the thing. So if you look at a matrix factorization in a neural network way, it's just do a linear mapping, okay? It's a linear transformation from a one hot vector to some like low dimensional space. But for text, what we need to do is try to use more advanced functions like deep neural network, CNN and RNN, okay, and map them into some feature vector. So essentially, for like users and items, we use like different functions, do the mapping to the same embedding space. And then based on that mapping, we can compute the similarity score between the two. Right? And then we can design similar loss functions. Like if it's explicit feedback, we probably can use kind of pairwise loss function. If it's like implicit feedback, then we can use this ranking-based loss function. So everything seems perfect. Okay. So what's the problem here? Computational challenge. Okay. So because if we just use this matrix factorization types of mapping, it's just a linear transformation, we only needed to use this much time. But for CNN, 10 times slower. RN, another 10 times slower. Okay, so efficiency becomes a huge, huge issue when the embedding involves some very complicated functions. So if we further break down the computations, we find that, because you see, here. So essentially we need to do the mapping and then do the dot product, right? So this is kind of feed-forward part. And if you do backward propagation, again, you needed to kind of do the derivative, go inside F and G. But anyway, the computation involves three parts. The first part is that some computation on the user side, so because you need to compute F of some U, right? I also need to do some computation on the item side, like G's of the content of the item, and also the dot product of the two. Okay, so if you look at the time units we need to compute each user, each item, and each dot product, we find that the most time costing one is computing the item-based node, because it contains context. We need to apply CNR and this kind of technique to it. So if you look at the traditional way to do the learning, essentially we want to design a mini batch, right? And for the mini batch, suppose we have those number of users, the number of items, and those number of like interaction between user items. The computational cost for that mini batch is going to the cost per user, okay, times number of user, and cost per item times number of item, and blah blah, right? So that's the cost model. So, and this is, since this TG is like sometimes 100 more expensive than the other cost, so this part plays the most important role in the computation. So somehow, if we look at this cost model, what we want to do is that for the mini batch, we want to reduce the number of items in that mini batch. Okay, so now how we can design a sampling strategy to generate this mini batch and make the computation as fast as possible. So remember what we are sampling. So for linear regression, logistic regression, we're sampling like standard data points, vector data points. Right now, what are we sampling? We're sampling links, the user item interaction links. Because when we define loss function, right, so we usually say, oh, in practice, this score function, we have observed a link or not observed this link, and the score function is blah, 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 and we want to minimize the score function in the 1, 0 or something like that, right? So the loss function is defined on those links, okay? So the data points here are also links. So where are the major computational costs? They are on the nodes, especially on the item types of nodes, right? So what we do is try to design some smarter way of sampling. So what are the existing sampling strategies? Let's start from negative sampling, which is so popular nowadays, right? The so-called negative sampling is that, okay, suppose for this mini batch, we want to keep B positive links, then essentially we just sample B positive links denoted as read ones. And then for each positive link here, we can identify a user, and then we sample K another negative items for this user. Because it's kind of completely random, so essentially, if we sample those links, they share nothing. Okay, so if you look at this mini batch, if there are B positive links, how many items are there? That's 1 plus K times B. That's the number of items, right? We're not happier, right? So we want to share items in a mini batch. So we're saying, why not we group by users, by items, okay? So in this mini batch, we can share a lot of items, right? So in this case, we group by items, and then again, we sample B positive links. And also we do a trick. For each item, we sample S positive link, okay? So in order to have B positive link here, how many items we need? So essentially, we have B positive link, but for each item here, we have S positive link. So it's here like 4 red links, right? For each item, there are 2 red link. So we only need 2 items. So in general case, it's going to be B divided by S. That's the number of items required. Okay, so compare this B divided by S and 1 plus K times B. That will be an easy speed up because we just need that tiny number of items. And later we find that we can do better. Why? Because here, if we do sampling this way, it's very difficult to define a pairwise loss function, because sometimes we say that with this particular user, this item ranks higher than some negative item, but there's no negative item. So there's no way for us to define the pairwise loss function. So then we do an even more extreme sampling. We sample B items, and we sample B positive links. So we naturally have B items and B users. And then for the remaining of the possible interactions, we treat them as negative links. So we do not sample negative link. We treat the remaining possible interaction as negative links. Okay, so here, how many items we have? Again, B. And here, we actually use much more links than the previous versions. What's the benefit of using more links? As I said, we are now sampling links. Links are the data points. So actually, we're using more data points. And as long as you're using more data points, actually, your learning algorithm will be more accurate. So later in the experiments, we will show that our performance is not dropping, but even is like improving because we're using more data points. Okay, so then what we can do is like we can also combine this group by items and this negative sharing. Okay, so in other words, we don't have to utilize that many items. So instead, we can just like first group by items, and for each item, we have like S positive sampling, and for the remaining ones, we treat them as negative ones. So this time, we have even smaller number of items. Yes?
So when you consider the rest as negative, doesn't that run the risk that, because there is the possibility that some of those links which are negative there,
Yeah.
they are in the positive range somewhere.
Very, very nice. So we initially have the same kind of doubts. So it's like if we treat all the remaining links as negative, then we could make some mistakes. Should we correct those mistakes? Actually, we do some experiments. We find the probability is just too tiny. It's not worth to going through all those negative links and correct them. Yeah, we just treat them as negative one. It's already good enough. Yeah. So initially, we indeed have that kind of doubt. Yeah, very reasonable doubt. Okay. So in a summary, right, so for different sampling strategy, this is a number of items we have, okay? So compared to the traditional one, this is our number of items in this new sampling strategy. So you can see, easily you can have a very big speed up. You can plug in some K and S, okay? So in our experiments, we find that easily you can get like up to 30 times speed up, just to try to change the sampling strategy for each mini batch. And interesting thing that if you look at the performance, as I said, especially for the sampling strategy using negative sharing, right? So the performance is even better because we're using more data points. Okay, so here it's like in real world it looks like this. It's convergence curve. So in the training part, our proposed free sampling strategy will reach a very good loss function, okay, at a very early time. For the other two standard sampling strategy, we need to wait for much longer time, and they do not arrive at the same good performance as ours. That's the training part. For the testing, similarly, at a very early stage, our algorithm can already have a very good performance, even better than those ones for the negative sharing kind of strategy. Okay. Okay. So any questions? Yeah, due to the time, probably just to give a summary. So essentially, for this part, the conclusion that we really need to look at a recommendation task in a broader view, in the information network view, right? And the additional information can really help to enhance recommendation, right? So, and also MetaPath is a very powerful tool to kind of regularize this information. When we wanted to differentiate what type of information we have, MetaPath is a good idea. And next, when coming to like more complicated collaborative filtering, like a neural network involved network filtering, collaborative filtering, sampling strategy becomes so important. Okay, so I think for that one, we just kind of begin the journey. Okay, there are a lot of things we can do in the future. Okay. Okay, question, yeah.
So for the CNN and the RNN you used, can you elaborate more what model exactly you used in comparison? You mentioned you used compare with the
Yeah. See, I think we provided some reference in the paper. So for CNN, it's just the standard like text-based CNN. For RNN, I think we use STM. So it's another like standard paper. Yeah.
So what's the output there?
The output would be the embedding. So we turn the like sequence of the text into a low-dimensional representation.
And then when you do recommendation and you do canon?
When we do recommendation, now we have embedding for a text and we have embedding for a user. Then we can define a score function, like using dot product. And then we can define loss function. So for example, ranking-based loss function or pairwise loss function to learn the weights, right? So what are the weights here? So for the user part, it's like we want to learn the embedding for the user, okay? For the CNRN, because like in the neural network, there are a lot of W, we're going to update those W, those weights in the neural network.
So So the lower level is only for the item part?
What
So the lower level you mentioned for
deep
the
neural network is just for the item part.
item embedded.
Yeah, because for the user country, we just treat that input as one hot encoding, or it can be considered as a traditional network embedding, because we do not consider content information for the user side. But of course, later you can say that we also have some content information, like the profile image, right? So.
Why you don't include the user level information?
So in practice, like we do not have this very complete information from the user side. And even we have some information is more like attribute information, is not content-based information. So still we can see it's a very good question actually. So it's like the computational cost. So here when we do the sampling, actually we leverage the computational cost difference. So in this setting, actually item-based computation is much, much more expensive than the user-based computation, right? So under this setting, we design our sampling strategy. So,
After you have the embedding for user and the item, then you plug back in the model you mentioned earlier?
right, so it's just a dot product to compute a score function, and then we can define a loss function based on that score function. Yeah.
The score function is the F in the model?
Score function is RUV, or score function is just dot product of the two.
I just want to know which model you are talking about this time.
Yeah, so because this method can apply to all kinds of models, so we just do a very high-level introduction. So you see, so now we have R. Once we have loss function, the score function between one item, then we can define loss function accordingly.
I see. So
Yeah.
this will just be like the ratings, for example, similar to ratings.
Yes, yeah. You can also be implicit feedback.
So this will, did you compile?
So probably we can talk this offline, okay? Because we still have a lot of things to go. Okay. We'll talk later. Okay.
The conversion performance, when you use a new sampling percentage, if you compare the conversion performance, that is with respect to time of with respect to the number of data points that each element has.
Can I say that? Is it this picture? No.
So
This picture? Okay.
Here is the time.
Yeah, time. War time.
If you compare the conversion performance between the algorithms with respect to the, let's say, epochs with the number of data points.
Whether I come.
Depending on the sampling algorithm, time to compute the scores are different.
You mean the performance, right?
Yeah.
So this is actually, if you look at the test plot, the y-axis is kind of performance.
No, I mean, okay, so I want to see the performance comparison with respect to not time axis, but the number of data points that each algorithm is using.
They're using the same data points.
No, but the number of data points that each algorithm sees per time is different because.
Yeah, this is war time, so it's like all things together. So so this is actually, I'm not sure whether this slide will answer your question. So the running time actually is the time required in a mini batch times number of mini batch that needed for the convergence. Okay, so in the previous analysis, actually we just say that for this mini batch, the time is going to be much better. Okay, but whether we need fewer or more iterations, right? So it turns out that if we use more data points, then we need even fewer iterations. So the speed up actually comes from two parts.
So basically what I'm saying is it's not just even faster than the other algorithm, but also it requires fewer data points.
The data points are still the same, so I still do not understand what do you mean.
You're generating new negative data points, right? Your new sampling percentage basically creates new negative samples between
The negative sharing, you're saying?
you generate new data point, which is not actually data set.
We're not generating new data points, we're just doing the...
I mean, you're deriving new data points because when you're looking at n data points, you're
Oh, okay, yeah. If you look at like a number of iterations, like for the negative sharing, actually we need less number of iterations. So that's why you can understand, yes, we only need to touch fewer number of data points. So I think when you're talking about data points, are you referring in this way? Probably you are asking this. Okay, I see. Yeah, yeah, because number of iterations means number of mini batch we need. So for negative sharing, actually we need less number of iterations. So essentially, we don't need to touch that many of data points.
Do you have any intuition behind why you need fewer data points?
It is because for each mini batch, if we use more data points, then we kind of only need like a few iterations.
Okay, so what about if you give the same number of data points?
Okay, so then I don't think if you are still interested in the exact number of data points, we still don't really do that type of experiments. We assume we can touch the same number of data points. Yeah. Okay. Any other questions? Okay. If not, I'm not sure whether we should have a short break, and I don't know what should be the right arrangement, because we have 3 parts of content, right?